Thank you, Amelia. Hey, everybody. I would like to switch back with my talk to the topics that we've had earlier today, computer vision and computer graphics. And specifically, I would like to hone in on one specific aspect of those, and that is how to use neural networks in high-performance contexts. So think of real-time rendering, real-time video transcoding, these sort of things. And I don't think I need to convince you a lot about why we should use neural networks for this, but just to establish some common ground, let me go over a few examples. First one, or the general thing being that, the general argument that neural networks are great function approximators with lots of recent successes. We're all familiar with them. They can compose text and music. They can generate images from doodles that a child can draw. They can generate images of faces out of thin air just using a random number generator. And they can play video games, actually something that wasn't touched today. And by now, these are old news, like 2017 AlphaGo and even AlphaStar, where an AI played a really complex strategy video game, is now a couple of years old. So lots of examples of neural networks learning incredibly complex, high-dimensional functions that mimic almost human behavior. And graphics people might object here that neural networks are actually way too slow. In all these use cases that I just listed, there are these big, heavy-handed objects that require data centers to run. You need a couple thousand GPUs, and you train them for a month. And then you get these amazing results. But if we actually want to use these things in high-performance contexts, how's that going to work? And here's the thing that's not actually on that many people's radar, and that's that neural networks can be amazing if you don't operate them at data center scale. So in computer graphics, we are interested in operating on much smaller functions, like, say, a 5-dimensional light field. Goes back to some of the things that Andrea talked about before, neural fields in general. And on these much smaller functions, we want to evaluate our neural networks millions of times, not just one single high-dimensional language query, but millions of queries to a lower dimensional function. For instance, you want to query that light field for millions of pixels to render an image. And it turns out that for these smaller functions, we can use much smaller neural networks. And those require much different algorithms to be performant. And that's really the essence of this talk, to take a peek at the use cases of smaller neural networks and how those can then be trained in mere seconds and queried billions of times per second to enable these real-time use cases. So I want to start with this 3D scanning example from casually captured photos. It's NORF, basically, for those of you who are familiar with it. And the problem setting is that you're given or you have taken a few photos of an environment you would like to capture. And to be fair, the computer needs to know the precise location of these photos. They need to be calibrated, one might say. But we are going to treat that as a given. We're going to say, computer vision people take care of that. We just know we have the photos, we have their poses. Maybe our phone's accelerometer and depth sensor gives us the poses. And then with those, we can run an inverse rendering algorithm that trains a neural network to represent this 3D environment right in front of our eyes. So this is now actually not a fast-forwarded training video, which is what you commonly see visualized. This is a tool running in real time. That's how fast the reconstruction would take. And they need to be clear that this was possible a year or 2 years ago already, but it would have taken you many hours. Like, you wouldn't have seen this happen within seconds in front of your eyes. So compared to traditional neural nets that train slowly on data centers, there's, of course, this advantage that the user of such a tool can immediately see the reconstruction forming. So if there's something that doesn't look quite right to them, they can go back to capturing a new data set. They can tweak their hyperparameters, click retrain, and there you go. They see the result right away rather than having to wait until the next day or, God forbid, the next week. And once this thing is trained, there's another advantage, which is you can interactively explore it in real time. And I need to reiterate here that because the neural network is so small and efficient, only because of that we are able to do this. For every pixel of these images that I'm rendering in real time here, we're tracing a ray into the scene, and along that ray we're evaluating this neural network that tells us for that position in 3D space, what's the color, how does it look like from my view direction. These are really billions of queries per second to produce a video like this. And then there are many other cool downstream tasks from an application like this, like, for example, virtual photography, where by editing the properties of this virtual camera, you get realistic defocus effects, you can frame your shot. This is not AI blurring the background, right? This is genuine ray tracing to produce the same blur that you would have seen in the real world if you had used a camera like this. And other tasks are also possible, like extracting feature buffers, density distribution, surface normals, 3D positions, or even a depth buffer. You can probably imagine that lots of downstream tasks can make good use of this, like slicing your environment. Even if you didn't have a green screen on site, right? You just take your phone, make a video of something, and then you can do this with it. All right. OK, hopefully that was motivating enough. In order to actually get to these small neural networks that are super efficient, I would say there are 3 main pillars that I found super important here. The first being, in order to make these neural networks small in the first place, like I said before, you need to have algorithms that are specifically tailored for small neural networks. If you use the same algorithms that you usually use for large neural networks, you're going to be a lot slower. And by tailoring the algorithms to those, it turns out you can get a 5 to 10x performance uplift versus using established frameworks like TensorFlow or PyTorch or other algorithms that are out there. The second pillar are hybrid data structures. And the reason we need those is that if you make your neural network much smaller, they're also going to be much worse at approximating the function that you want to approximate. So in order to combat that and give them back some of their approximation power, it actually makes sense to develop data structures that work in concert with the neural networks. And what we did specifically here, what I think is interesting to look at, is something called a multi-resolution hash table. You're probably mostly familiar with hash tables as a general data structure, but it turns out to be very useful in spatial computing, and that's what we'll see later in more detail. They're actually also very fitting to modern GPU hardware that you have all in your phones by now and in your workstations. The third pillar are the rendering and training algorithms that actually use the neural net themselves. So basically, many of our existing computer graphics algorithms are built with this understanding that the lookups from an underlying data structure are fairly cheap. Like normally, you would represent your 3D environment as a grid of voxels, or you would represent it with triangles. Again, think of the visualizations that Andrea provided before. And neural nets are, for each individual lookup, much more expensive than these other data structures. So in this case, we really want to tailor our rendering algorithms, or whatever makes use of the neural nets, doesn't have to be rendering, to make as few queries to the neural net as possible. So in this example of volume rendering, where you march along your array and you query the neural network, you might want to have some additional data structure that skips all the empty space until you hit the object and only then start querying the neural network. And after you queried it a bunch of times, the rest of the array is basically occluded by what it had before, so you also want to skip those. So by tailoring the algorithm to that, again, it turns out you can get up to 100 times fewer queries than naive tensor-based algorithms you might implement. And now, the best thing about these 3 pillars is that their benefits compound. This is often not the case when you're optimizing algorithms. But in this case, we have 100 times fewer queries to a neural network that's 10 times cheaper. So that's a 1000x overall multiplicative. And then by having these data structures, you can actually get approximation power that's on par with much larger neural networks that you had run before. And that's really what makes this combination of pillars a game changer, while every individual one would not have been necessarily. And I want to actually dive a bit deeper into the algorithms that underlie the small neural networks first. So what we're going to talk about is a specific type of neural network, a multi-layer perceptron, MLP for short. And this means some number L of fully connected layers, M neurons each. And what we consider to be a small MLP, think something like 2 to 6 layers deep, 32 to 128 neurons, not so many each. And if you're not familiar with what exactly this means, don't worry. It's not so important for understanding the main point. I just want to throw out ballpark numbers for those people who know MLPs. Important is that evaluating such an MLP on a batch of elements, so on your set of pixels, for example, is simply a sequence of short and wide matrix multiplications. Short, because every row of these matrices corresponds to a neuron, and we are saying that we don't have so many neurons. And wide, because every column of that matrix is one element in your query batch. So for every pixel of your image, for example, you would have a column, and there would be millions. So 32 times millions matrix is sort of the dimension. The compute cost of these matrix multiplications scales with the square of the number of neurons and the memory traffic of this thing scales linearly. And normally, common sense of algorithm engineers would dictate that then you need to focus on compute, because that's the expensive part. But when you have few neurons, the complexity class actually doesn't matter so much, and the constant factors start to dominate a lot more. So for these small neural networks, it's the complete opposite than what you would typically expect in a machine learning framework. You actually care a lot more about memory, because the constant factors are on modern processors that memory lookups are many times, like 1,000 times more expensive than to compute things. And just to illustrate what has to be changed on the algorithm in order to be more efficient on modern GPUs with these small neural networks, let's go through the execution of one of these neural networks that would typically happen in a big machine learning framework, step by step. So first, you load all the inputs from RAM into your execution units. Then you perform the matrix multiplication on all these inputs that you just loaded, and then you write that result back out to RAM. And the entire GPU participates in this. It basically parallelizes with all its cores over that particular matrix multiplication. And then after it's done, it loads the results that it just computed back from RAM, applies an element-wise activation functions like a ReLU, and then writes the results back to RAM. And then rinse and repeat. Like every time the GPU loads everything from RAM, parallelizes over that one computation, then writes everything back to RAM. And this back and forth writing from and to RAM is really the memory bottleneck that I've been talking about before. For small neural networks, that's where the majority of the cost lies. And the key idea here is because these matrices are short and wide and not tall and narrow like they would be for other machine learning tasks, we can dice this entire computation up into individual chunks. And now it turns out that when these individual chunks are small enough, the intermediate results don't need to go back and forth to RAM. They actually fit into the caches of every individual core of your GPU. And so one core of the GPU can do the entire neural network computation from top to bottom without talking to the rest of the GPU, without going to RAM, and that saves all of that memory bandwidth. And on top of that, the GPU can parallelize across all of this. And now, conceptually, this seems very simple, but it turns out it has a really positive, really good effect. We call these fully fused neural networks owing to the fact that there are no back and forth from onto RAM. And those of you who are familiar with this concept of operator fusion, it already exists to a degree in machine learning frameworks, but not to this full degree that the entire neural network gets fused. That's why it's fully fused. And again, it only works when the network is actually small enough so that these chunks fit into caches. But once you have this, the difference that it makes is striking. So here I'm showing you throughput of this alternate implementation in green versus the baseline TensorFlow in red. And on the left side, I'm showing inference performance. On the right, I'm showing training performance. And both of these graphs are parameterized over batch size in the bottom. So they show the throughput number of elements processed per second for different batches from left to right. And for inference, we're actually interested in large batch sizes because we are interested in processing large amounts of elements at a time, every pixel of an image, and that can be millions. So we can parallelize across all of that, and we get 8.6 times of a speed up. For training, the opposite is true. We actually, surprisingly, want small batch sizes, and that's because if you have a fixed amount of training data, you can train better if you do many small optimization steps over little chunks of that data rather than a single large optimization step over that entire data. You want to maximize the number of steps that you have, sort of. So you prefer to work on smaller batches. And in that regime, that's the left-hand side of the graph, it's a 9x performance uplift. So overall, 10x, 5 to 10x is roughly the ballpark. And yeah, by the way, if you're interested in trying this out, this is all open source. It's basically a little custom machine learning framework that we've built. But you can call into it from within PyTorch if you prefer to stay in the Python ecosystem. So that's all available if you want to try it out on your problems. And that's actually all the magic that's behind these fully fused neural networks. Just a small algorithmic change, and a myth is dispelled that neural networks have to necessarily be slow. What we are going to look next at is these multi-resolution hash tables, this hybrid data structure. How we can get back the approximation power of the neural networks after we shrunk them down. And in order to talk about this, I should first mention input encodings, because the data structure will follow sort of the same idea. And input encoding is basically exactly what it says. It encodes the inputs to a neural network into a sort of different form, such that the neural network has an easier time processing them. And what's interesting about those is just how effective this strategy can actually be in practice. So I'm going to go back to the NERF use case. We're going to convert a few dozen images with known camera poses to this neural network that can predict what the color is based on a position and view direction query. And we're going to just train it live in real time. So if you just use this neural network, moderately sized, 10 layers, 128 neurons, we see something rather quickly, right? This is good. It means at least we've got the speed down now. But the quality is really, really poor. And now let's introduce an input encoding, a so-called positional encoding that is surprisingly effective at improving this situation. We have the exact same neural network here, right? But we transform its inputs with this very simple equation that looks like this. It's just a bunch of sine and cosine functions applied to it at different frequencies. And by doing this, it turns out that the neural network is able to create this much, much, much better 3D reconstruction. I just find this astonishing. It's a very simple change to the algorithm. It's one line of code. It's essentially for free, performance-wise. It doesn't cost you anything. And there's such a big improvement. So the simplicity of this and the large positive effect that it has basically raises the question of when we actually do something slightly more complex than a few trigonometric functions, whether we can get more out of this. And that's where the data structure comes in. So yeah, with the data structure, training happens even quicker. It converges to a better quality. And I've been a bit sneaky. I also made the neural network smaller. So it's now only 4 layers instead of 10. It's 64 neurons instead of 128. And that's because this data structure actually takes on part of the learning task. And so the neural network doesn't need to be as big in order to have the same approximation quality. And that gives you this additional speed bonus. I think in order to explain the data structure, this is probably the most low-level and technical thing I have in the talk. I will just go step by step through the algorithm, and then it should make sense. So in these sort of neural graphics primitives and high-performance graphics tasks, the neural network is usually tasked with predicting a function of a spatial component and then maybe some other input variables. But the spatial component is usually there. And the data structure will focus just on that spatial component. So it would be a 3D position for light fields, or it could be 2D if we're operating on images. The example is 2D for obvious reasons. And now the goal of this data structure is to represent complex spatial variation in that positional variable so that the neural network later on can focus on all the other higher dimensional parameters, because neural networks are usually good at predicting these higher dimensional components. So in order to learn some parameters in 3D space, we're going to place them on the vertices of multi-resolution grids. They are visualized here as a 2x2 grid in blue and a 3x3 grid in red. So what you can notice here is that the textures, this is basically the same as volume textures, or in 2D it would be regular textures that are superimposed at multiple levels of detail, multiple resolutions. And we will now train parameters that we place on the vertices of these grids using gradient descent. The reason for superimposing these different levels of detail is that most graphics tasks can actually be decomposed into different scales. And by simply having all kinds of scales available to the training process, it will automatically figure out on which scale to put which part of the signal. And the main challenge is the same as with classical grid-based approaches, and it's, frankly, size. Right? If you want centimeter scale detail on a kilometer-large game level, for example, then you will not have enough memory to store all of these centimeter-sized little blocks. And so instead of that, we're going to use a hash table of grid cells instead of representing these grid cells all on their own. So let me just walk you through a lookup from these hash tables. Again, just going step by step through the algorithm makes it easier to understand, I think. So given a position x, we're going to figure out the cells that we are in, and that's just a little bit of multiplication by the resolution, conversion to an integer, rounding up and down. That gives you the integer vertices of the cells. And then we're going to compute something that's called a spatial hash for each one of these corners. So for example, the top left corner of the red cell might have a spatial hash of 2. and the top right corner might have a spatial hash of 0. And the same is true for all the other corners. The important thing is the hash is a deterministic function we can easily evaluate for all of these corners. These hash values will then give you indices into hash tables, one of which we create for every one of these grids. So the question is, why should we do it this way? Well, first, there's no control flow divergence in this process. This is what GPUs are good for, right? To look up a value from the hash tables, we derive a memory address from it by computing a hash, and then we look up the memory. That's it. Every GPU thread can do that in parallel. You don't need a tree data structure or pointer chasing or anything to figure out where from these hash tables in memory you're supposed to look up something. Another advantage of hash tables is that they give us an easy, predictable way to trade quality for memory usage. So you can just make the hash tables bigger or smaller if you want to. It's completely decoupled from how large your scene is and how fine you want to tessellate it. And lastly, I think this is the most important point, this scheme is completely task agnostic. It will automatically exploit sparsity in any kind of task. And I know that that's a steep claim to make, so let me try to give you some intuition for why this is the case. Think of what happens when your hash tables are too small for the amount of elements that you want to put into them. They're going to be collisions, right? So in this case, for multiple different little boxes in 3D space, for multiple different cells, they're going to hash to the same place in the hash table. So when we actually want to optimize what the neural network puts into that hash table in that place, the gradients of all the colliding positions in 3D space, these gradients are going to add up to that singular location in memory. And because they add up, the gradient that is strongest, the one that is most relevant to the loss function, will dominate that addition process, and that will be prioritized. So just by doing gradient descent over colliding positions in 3D space, it turns out the computer under the hood gradient descent does a sort of a majority vote which 3D positions should be prioritized to minimize the loss. And that's really regardless of what kind of application you throw this thing onto, whether it's image compression or NOVs or signed distance functions, it will always prioritize whatever the loss function wants and does automatic collision resolution that way. So really, unlike regular hash tables, you don't have an explicit collision resolution mechanism in there. OK, once you've actually figured out your hashes for the corners, looked up the corresponding values from the hash tables, we actually want to linearly or in some other way interpolate the lookups from the corners that we've just made. Because if we didn't do that, if we just looked up a single value per box, then we would actually learn a very blocky function, right? It would be discontinuous. And this interpolation process gives us back spatial continuity. Think of it like texture interpolation. And of course, remember, these hash tables, they only take care of the spatial coordinate x. All the other inputs that we want the neural network to have, they can just get concatenated below after whatever we've looked up. And then that is what we're going to feed into the neural network. And that's actually it, right? That's all there is to this data structure. You can take this rather simple computation graph, you can plug it into any high-performance graphics application that can benefit from function approximation and neural networks, and you're good to go. You can really train this thing end-to-end with gradient descent. So now let's look at a few applications where all of this machinery is actually useful. First one is going to be representing images, probably the simplest one. You can think of an image as a 2D function from a position on the image plane to a color value, right? And so that means that in order to make this into a neural graphics primitive, we just need to learn that function with the hash table neural network combo. And because regular images are rather boring, let's use this special photograph by Trevor Dobson, which has I'm not sure if you can read it down there. This has a resolution of 56,000 pixels times 21,000 pixels. So that's over 1 billion pixels. And what this means is that we can zoom in, and then we can zoom in again, and then you can read the writing on the street signs. So that's a very small slice of this overall image. And that makes it a challenging image to approximate using a neural network. Now, there have actually been some papers that tackled this problem before, and those took a couple of hours, let's say 10 hours, to fit this image with a good approximation error. But we can now do it in real time. So let me switch to a live training video. Don't blink. Yeah, there you go. That's it. For normal images, it would have been fit in that short 2-3 seconds. But for really complicated images like this one, it takes a bit of time for the really fine-scale detail to converge in and for the street sign to become legible. But even now, after like 15 seconds or so, you're starting to see some of this detail. And at this point, you can start asking whether this could become some new kind of compression mechanism at some point, because the neural representation, even with hash tables, is quite a bit smaller than if you represented this image in uncompressed form. And I really have to make clear that I'm not suggesting this will replace JPEG anytime soon. Like, there are so many rough edges here, and it's still orders of magnitude off in terms of performance, but it's at least in the ballpark where you can think of compressing things with this. OK, let's jump to another application, which would be signed distance functions. They're a way to represent the shape of an object. More specifically, they map a 3D position x to a positive value if that 3D position is outside of the object, to exactly 0 on the surface, and to a negative value inside of the shape. So the 0 crossing of this function is the surface of the object, and the neural network is tasked with learning this function. And just like before, let me show you a live training video of an example signed distance function. 3, 2, 1, there we go. And again, within 2 or 3 seconds, the neural network already converged to a somewhat reasonable approximation of the shape. And just to show you the function network actually learned, here's a 2D slice through this thing. The neural network learned to be negative, that's red on the inside, green, positive on the outside. And the decision boundary is really the thing that I've been visualizing and rendering just now. And even on more complex shapes, this mechanism or this machinery that we've discussed before is doing quite well. And that's, again, because the hash tables are able to focus all the collisions on this relevant surface 2D manifold of the objects that we're learning. Right? The signed distance function is very smooth far away from the surface of the object. In the green or the red regions, it's only in the decision boundary where there's lots of high-frequency detail. And hash tables plus neural networks able to focus on that. There's another cool application, which was actually for the research that I've been doing in the past, the main use case I've been thinking about when developing the machinery. And that's global illumination. It's useful in visual effects and movies. It's useful in video games. And all these other 3D reconstruction algorithms like NOVs and signed distance functions were more of a happy accident that popped out on the side after looking at those. So global illumination refers to light that reflects off of objects many times before hitting the viewer's eyes. So simulating these interreflections is absolutely essential in obtaining a realistic-looking image. And in order to show this, let me put on the left an image rendered with a direct illumination, which only considers a single reflection of light. And as a consequence, it looks flat, has 2 dark shadows. And as you can imagine, this is, however, much faster to compute. Right? A single reflection of light, much, much quicker than computing multiple reflections and then averaging the results of many of those. And that's why direct illumination was the algorithm of choice for video games until very recently, actually. The only reason that video games didn't look like this is because we had a figurative army of artists that slapped on a variety of hacks and basically cheated this look of global illumination. Like they would paint in soft shadows and do other crazy, unspeakable things that you don't want to know. So nowadays, though, our goal is to actually compute global illumination. We have beefier GPUs, better algorithms. We want to do it in real time in order to free up the artists to actually work on interesting things, to make content, to be creative, and so on. And for user-generated content games, like let's say Roblox or Minecraft, users don't know how to fake the look of global illumination. They build something and they want it to look correctly, right? So basically, we have no choice. Global illumination it is. And the way to compute it, at least at the moment, is with path tracing. You simulate billions of possible trajectories of light, and you average their result in order to generate a single image. And, then you want to do that at 60 frames per second. What could go wrong? And this brings us back to neural networks, namely the idea that we would like to just cut these paths short and then ask a neural network to inject global illumination into the ends of these shorter paths in order to save lots of compute cost. So basically, at the end of these paths, you take the position that you ended up at, the direction from which you came, maybe material information and so on at that point, and you pass that to the neural network, and you ask that to predict global illumination at those points. And again, only because we've developed this machinery to have neural networks that run so much faster than typical ones, are we able to actually run this inside of a real-time path tracer that you might find in a video game. And show you how this might look like in the real world. So on the left, you see the image produced by a fairly advanced path tracer. And the right one is the image that you get by adding this neural radiance caching mechanism that I just described to that path tracer. Now, these images look grainy because we are not actually simulating enough paths. Like in reality, you simulate lots of these random light paths, and by averaging enough of them, at some point the noise converges away and you get a clean image. But the reason you need to simulate so many paths is just that light can bounce in so many different ways, and you need to average or integrate over all of those. Now, the important thing in this comparison, the reason that the right image looks better, is that with the neural radiance cache, this end of the path, the stochastic portion of the image generation process, is replaced by a smooth neural prediction. Right? That means there's a lot less variation overall, and that's why the image is cleaner. Or conversely, you can also interpret this as the right algorithm being 50 times more efficient or 50 times as fast as giving you an image with the same noise level as the left one. And I personally find this very satisfying because normally this is not the way it goes. Normally, if you introduce a neural network into an algorithm, it doesn't get 50 times faster. So a very pleasant surprise. But the best thing I didn't even mention yet, and that is in the result I've just shown, the neural network is not actually pre-trained on that level, but constantly trained on the side while rendering is going on. And the reason for that is that in video games, your environment changes unpredictably, right? The player might do anything. The enemies might do anything. And so you need to constantly train the neural network and update it with current lighting information. If a door opens, it needs to learn that light comes in through that door. And so online training is a must. And the way it works is that you can select a subset of the paths that you already traced for rendering anyway, and then you extend these few paths just by a few additional bounces like this, these 2 blue extra bounces. And just like before, you can ask a neural network to inject global illumination into the end of that elongated path, and then propagate that radiance back along the path. And now we can say, well, the light that arrived at all the previous vertices of the path is now our training data for the neural network, turning this into a sort of self-training algorithm. You can prove that it's solving the right integral equation that corresponds to light transport, so this works out, this turns out correct. And what I personally find very interesting, but I should probably not get too deep into, is that this resembles Q-learning a lot. So this is a strong suggestion that, at least I hope, a similar algorithm with small neural networks could also be useful in reinforcement learning contexts more broadly. Okay. Let me just emphasize again how much of a necessity the speed of the neural network is here. Basically, the performance envelope for real-time graphics in computer games is incredibly tight. And even this optimized path tracer that I've been comparing with is pushing the limits of it with 11 milliseconds. Like in modern video games, the budget for lighting is usually 3 milliseconds or so per frame, 3-4 milliseconds. By using the cache, of course, we're cutting the paths a bit shorter. That saves some compute. And there's 3 milliseconds saved by making the path shorter. That's not that much, right? And in those 3 milliseconds, we would like to both query the neural networks and also train them. So yeah, normally it would be unthinkable to do that on 2 million pixels, right? 1080p frame at 60 frames per second, and then also train it in that short amount of time. So it's an argument for all the machinery we developed before. And now to finish it off, let's go back to 3D reconstruction with nerves. That's the example that you've seen in the beginning of the talk as well. And in this case, what the neural network does is it learns this mapping from 3D position and the view direction to color values and density values at that position. And this is trained through this rendering procedure, or inverse rendering procedure in that case, where you march along rays, you evaluate the neural networks a bunch of times, and you aggregate the results along the ray to produce pixel colors. And inverting this, turning it into an inverse renderer, is what gives you the training process from images to 3D. So you've already seen how fast these reconstructions are, so I'm just going to show this quick collage of 8 examples and move on. And what I want to do is show you a few really cool reconstructions that popped out of working on all of this. So this factory floor, for example, which was reconstructed from just a casually captured iPhone video. And like I said in the beginning of the talk, like you could have gotten these 3D reconstructions 2 years ago already. It's just that it would have taken you a day to train this thing. And then every single image you would want to render would have taken you a minute each. So it's such a game changer to even a researcher's workflow working on this, where you can walk around, record a data set for fun, and have a good result pop out instantly. It makes you so much more productive and more than makes up for the extra time that is spent actually implementing a more involved algorithm under the hood rather than jumping straight into the Python frameworks. And what really opened my eyes to just how important this sort of interactivity is when artists all around the world started downloading our research code and went through this grueling experience of trying to compile it on their machines, CMake and CUDA and different compiler versions, just to be able to work with these. So we ended up polishing things up a bit more. We started a competition where people were asked to make their favorite reconstructions and submit them online to win graphics cards, and this turned out spectacularly well. Like we've had submissions like this. We have this one where people created pocket worlds by compositing different reconstructions together. And here's a favorite of mine, which is, it turns out, when you have mirrors in your room, it's easiest for the neural network to create parallel worlds. Like it doesn't want to make reflecting light. It really just duplicates everything that it sees through the reflective surfaces. So that one's really fun. And then this one is actually one that I recorded myself when I was on a vacation in Japan to hang out with people that I programmed a game with in a past life. And you can see we're nerds because everyone is glued to the laptop. We basically traveled the country. We rented these traditional guest rooms. We hacked on interesting problems together. And we fooled around, of course. So this is Dean. What he's pointing at is a Matrix parody that we watched together. And through the window here, you can see an outside bath with actual Japanese hot spring water, so that was pretty amazing. And now, please just imagine taking your own photo collections and creating these sort of reconstructions and sharing them with your family and friends this way. I just love the interactivity of it. And I think it's super duper cool that working on something as fundamental as accelerating neural networks and fusing them with a data structure and so on leads to really truly usable and worthwhile use cases like this one. Think also of looking at restaurants before you visit them, like from Andreas' slide before. Think of replacing Google Maps or Google Earth with this. There are so many cool use cases that come out of this. So I think it's time to conclude now. I want to briefly revisit these 3 pillars because I think they're really important, right? We've seen that neural graphics primitives can be trained and queried basically instantaneously by, first of all, shrinking the neural network down and then using algorithms that actually caters to the different requirements of these smaller neural networks. But then these smaller neural networks are worse at approximating things, so we had to introduce this hybrid data structure, multi-resolution hash tables, that are going to be trained jointly with the neural network in order to bring us back the approximation power. And lastly, it's important that the algorithms that you actually apply this to are rethought to make good use of these efficient neural networks, because as efficient as you make them, you still want to minimize the number of queries that you actually throw at them. But once you did all of this, there's this compounding benefit, right, where these different pillars multiplicatively improve your performance, such that you can outperform the classical state of the art, not just necessarily in quality, but sometimes even in speed, like with this neural variance caching thing that became 50 times faster. So my personal key learnings from this entire train of research, which I think are probably good takeaways from the talk, would be the following. And the first one is that a neural network combined with a generic data structure results in this surprisingly versatile algorithm, not just when you scale it up to gigantic data sets and use data centers to train the thing for months, but even when you train your neural network locally on your machine, or maybe at some point even on your phone, from a bunch of photos that you've taken. And what I've not said before, but what I think is really cool here, is that I've used the exact same model with the exact same hyperparameters for all of these different use cases and applications. So usually you have very different algorithms for processing and distance functions and for images and for 3D reconstructions, but here it's one and the same, even the same hyperparameters. And they were sort of in this happy equilibrium that gave good results in all of them. Next really important takeaway, and this one is I mean, everybody knows this. Make sure that you are aware of your constraints and that you always question what's going on, think outside of the box. As scientists, we are really encouraged to think this way. But it's just so easy to fall into this trap to accept that, neural networks, they're pretty slow. I shouldn't use them in graphics. And then, I was pretty stubborn in my PhD days, and I did use them in graphics, and I waited many hours to train them every single time. And I could have saved all of these hours if I had just tried implementing myself with the right mindset earlier on. Now, the last point that follows a bit from this is that I think full-stack expertise really pays off. Like, don't be afraid to delve a bit into C++ and CUDA and other things, not just Python, because sometimes your bottleneck is actually not your coding speed. If your bottleneck is the coding speed, by all means use Python. We used Python to instrument all of our experiments that went into papers in the end, right? There's no need to use low-level code for that. But for actually writing the bottleneck part of your application, waiting for training every single day for many hours, even if you spend 2 weeks implementing that in a slightly more complex fashion or a month, can really pay off if then you can iterate every 5 minutes instead of every couple of hours. So yeah, know to use which tool to use in which context. Python for high-level stuff, but consider the lower level languages at least for the lower level stuff. And that's pretty much all I have. Thanks for listening.
Congratulations. We have time for one question. We have time for one question right now. So if you have one, please raise your hand. And then also remember that we do have a panel session coming up. So if we don't get to your question right now, maybe save it for then. So can I take a question from the audience? Yes, we have one right over here. Thank you.
So hi, my name is Altai. Thank you for your presentation. I have a rather technical question. I hope that's okay.
Sure.
But could you please explain the multi-resolution hash tables a bit more? Like, what is the benefit of having the multi-resolution? Because from what I understood, we just take the final encoding and give it as the input to the network. Like, do we somehow ignore empty spaces, or is there any tricks like that?
So you can think of the multiple resolutions as signal decomposition, right? Like a Fourier transform almost. Like every signal that you have has low frequency and high frequency components. And the low frequency grids, or the coarser grids, will be better at representing the low frequency components, or at least they will be more parameter efficient at doing so. And the higher frequency grids will be better at representing the higher frequency components of your function. And so by just superimposing all of them, you are making sure that whichever resolution might be most worthwhile for your task, or whichever combination of resolutions is there, the learning algorithm has these at its disposal to put parameters in there. So it's kind of making sure you're covering all the possible things that you might want. In specific use cases, you might be able to get away with single ones, but there's not much of an overhead to just have all of them at the same time.
All right, I see. Thank you.
Thank you. One more time for Thomas. Thank you.
Thank you.